separation of variables. We've talked about it sort of informally before, but let's look at the actual technique then. So we're looking at first order differential equations. It will be separable if it's possible to write the derivative this way, some function of x times some function of y. Because then you could rewrite that as something like that. Bring the function of y to the left-hand side, but then move the dx to the right-hand side. We can get our integral. Everything's fine. Now, we have to be careful with this method. You see, if function y equals 0, if that's possible, then we get what's called a trivial solution. Because think about what you're doing. You're dividing by function 1. Well, theoretically, you're dividing by 0, which of course you're not allowed to do. So it will create the trivial solution. So you just need to keep an eye on that. Okay? So it's easy enough to check. You just look at the function y and you say, well, is it possible for this to equal 0? In which case, if it is, you say, oh, okay, well, this may well be a trivial solution. Okay, x squared 1 plus y squared. Let's rearrange it. Now, of course, when I do the quick check here, 1 plus y squared, well, no, it's not possible for that one to equal 0. So we're not going to get any trivial solutions. So let's integrate. Left-hand side, what do we got? That's an inverse tan function, isn't it? So we'll get inverse tan of y is x cubed on 3 plus some constant, of course. Let's make y the subject, so we'll just tan the other side, if you like, and we get tan of x cubed on 3 plus a constant. So a little bit different to what we're used to seeing here, because our constant is no longer just plus a constant, it's actually within the tan function itself. Okay, y dx equals x squared y. Now in this case, we have got a trivial solution, because it is possible that y could equal 0. And look what happens if y equals 0. If y equals 0, it makes the y dx equal to 0. If you integrate 0, you get a constant. So therefore the solution y equals 0 is certainly possible. Let's now work out the other possible solutions. Integral of dy on y is the integral of x squared. So left hand becomes log. So log of the absolute value of y is x cubed on 3 plus some constant. So I'll exponentialize. So absolute value of y is equal to e to the power of. But of course I could use my index laws and break that up to be e to the power of x cubed on 3 times e to the power of a constant. Well, e to the power of constant is a constant. So I'll just rewrite it as constant times e to the x cubed on 3. And that constant happens to be e to the power of c. So in this case, we know we're dealing with a positive constant, which is good when you think about it, because absolute value of y, we'd want it to be equaling a positive number. But I can make it y equals, I've changed the c to an a, because now what I'm saying is, well, it would be possible. A could be a negative number. You see, it is possible for y to be negative, because we're saying the absolute value of y is equal to this. So you could have a negative number for y. So y is equal to ae to the power of x cubed on 3. But my final solution is, well, actually there is also this trivial solution, y equals 0 as well. That would be a possible answer. Ooh, we've been given an initial value. So y, when x is equal to 1, is pi on 4. We've got cos y on x squared. Similar to what we were doing in other integration, if I've got an initial value problem, I'm going to go with definite integrals rather than trying to find constants and things like that. So it will become this. Now, I'm dividing by cos squared y. But cos squared, the reciprocal of cos squared y is, of course, sec squared. So on the left-hand side, we get sec squared. Is it possible that cos squared y was equal to 0? Oh yeah. But I'm dealing with a definite integral here. So when I sub the values in, if I don't get the answer 0, it's not going to be an issue. Equals the integral of dx on x squared. And the limits they told me, when x is 1, y is pi on 4, I'm trying to find a relationship between x and y. So integrate sec squared, we get tan. Integrate 1 on x squared, we get minus 1 on x. Substituting in, tan y minus 1 is minus 1 on x plus 1. Rearranging all that, making y the subject, I get the inverse tan of 2 minus 1 on x. Ah yes, this example here. when you look at this, it looks like they're not separable. Because how am I going to get this y squared to the other side? Because it's over 2x squared. And how do I do it? So the first instinct is to say, well, hang on, this is not separable. But it is. Instead of looking at it as function x times function y, if I look at the whole thing as actually it's a function of y on x, you see, I could rewrite that to be a half plus a half of y on x all squared. If I do a substitution, u equals y on x. So in other words, y is equal to u times x. But remember, when we do a substitution, we've got to do a complete substitution. So the y dx will become now u times x. But remember, u is a function of x as well. I've got to use the product rule when I differentiate here. Write down the first, u. Diff the second, x. Well, differentiate x, you get 1. Plus, write down the second, x. Diff the first, well, du dx. This becomes my new differential equation. U plus x du dx is equal to a half plus a half u squared. That I can rearrange, and I get that x du dx is 1 minus u squared over 2. But now I can separate those variables. And I get 2 lots the integral of du on 1 minus u squared is the integral of dx on x. Okay, integrates those. I've got 2 on 1 minus u is the log of the absolute value of x plus a constant. I've rearranged that and made u the subject. So let's get y back in there. U was y on x. So y on x is equal to 1 minus that. Multiply out by x, and I have an answer for that particular derivative. So that one's a little bit trickier because you need to manipulate the algebra in there a bit to come up with a result. 13C, time to do some separation of variables.